Hi everyone. So my name's Alan Green. I'm a researcher at the Sustainable Buildings Research Centre. It's really interesting for me to be here today. I'm enjoying the conversation on all of the topics. So at the SBRC we research how to make buildings more sustainable and resilient to natural disasters. So my own research covers bushfire sprinkler systems, but also things like mould growth and condensation in buildings and thermal performance of buildings, so building physics in general. Bushfire sprinklers, as you probably know, are being used by people, but there's very little guidance on how to design these systems properly. So from our research, we know that many households are using them. So I've been researching them for about 10 years, and even during that time, I've seen a lot more proprietary systems coming to market in Australia and overseas. But those proprietary systems and the systems people are designing themselves are of varying levels of sophistication, and a lot of them are arguably not fit for purpose and quite dangerous. So it is important to understand, I think, the fundamental principles and what we do know and what we don't know about these systems if you're going to be relying on them. We see that these types of sprinkler systems are often combined together with passive measures, which is a good approach. So it's not a silver bullet. When we talk about active measures, that's usually sprinkler systems, and passive measures are other features or retrofits you can make to your building to protect it from bushfire, like screens over windows, sealing gaps that might allow embers to enter, those sorts of things. We do have an Australian standard on how to design bushfire sprinkler systems, AS 5414. It's currently under review. It's probably the most detailed design guidance available in the world on how to design these systems, but it still is lacking in many respects. And so hopefully through the review it will be improved. So bushfire sprinklers aren't yet acknowledged in the National Construction Code, the NCC, which dictates how new buildings need to be designed and built in Australia, or in AS 3959, which is the Australian standard that dictates the bushfire protection measures for new buildings. Because of all of this, what we see and the repeated feedback we get from community when we're working with people in the community is that the guidance that's available on how to design these systems is really lacking currently. So to give it just a rough idea of how prevalent these systems are, this is just data from one community that we worked with, Kangaroo Valley, and leading up to the Black Summer bushfires, there were about half of the sample that we interviewed and did building assessments for that had some form of bushfire sprinkler system installed. So they are being used by a lot of people. It's not really a marginal technology. Yeah, so we can go through this in a bit more detail. So we saw that most or all households, so the horizontal axis is the proportion of the total sample that we're undertaking those measures, and it's split into the households that evacuated and those that stayed to defend their property during the fire. So up the top, most people or all people were moving outdoor furniture away from the buildings, clearing vegetation, doing those sorts of preparations, and then watering the lawn or garden. Then bushfire sprinklers were the next most common. And then moving further down, you see the more sort of in-depth retrofits where they're putting screens over glazing. We can't say from a sample or a study this small what did and didn't work, but we have pretty good evidence from a host of previous fires looking at which buildings do and don't burn down. The evidence shows that bushfire sprinklers can complement and help, but some houses with sprinkler systems still burn down, and likewise some buildings with all of the passive measures that are recommended still burn down. We know what helps, but there's no guarantees. One big challenge with active systems is they're more reliant on, they're more complex, so there's more that can go wrong. So if we look at the process of how you would design a bushfire sprinkler system, the first question is how much water do you need and where does it need to go? And so the first step is really identifying the vulnerable features of your building that you want to protect with the sprinkler system. In a lot of cases, we see people just putting sprinklers on the roof without thinking too much about what that is actually going to do for the building. Whereas a better approach would be to look at the building, identify which features can be protected better by passive measures and doing that first. And then if there are some features that could do with some extra protection, that's where a sprinkler system could be a good feature. what you really don't want is to put in a bushfire sprinkler system and then feel like you have to stay and wait later than you should be before evacuating so that you can activate the system. That's something you really want to avoid. So some of the science backing up the design of these systems is still evolving, and we don't know things with much certainty, but what we do know with certainty is that if you're designing these systems, you should have an independent water supply, and you should have pumping capacity or a gravity-fed system, which is going to operate without power as well. It's in the hundreds of thousands of litres. Yeah, and it depends on what you're designing the system to do and how you're planning to activate it, whether you need to activate it extra early so you can evacuate. Those sorts of considerations can change it quite a lot, but it's in hundreds of thousands. And so that's another reason why these systems are not a silver bullet. It's not something that every house necessarily should have, but it could be a useful technology in certain situations. So that, in terms of conserving the water, things like that intermittent operation, so turning sprays on and off, or zoned operation, where if you're there operating the system manually, you could turn sections on when needed. Those sorts of water saving strategies can be really helpful to cut down on the storage requirement. One of the main points I guess I'm trying to communicate is that the science supporting these systems is still evolving. So if we think of indoor fire sprinklers, they are supported by decades of research and experience, and there's hundreds of Australian and international design standards which show us how to design those effectively, whereas bushfire sprinklers, there's a handful of studies that have been done. So we're really in the early days of understanding how best to design these. That really comes to the fore when we look at answering the question, how much water do we need and where should it be sprayed? We do know that you should be targeting your vulnerable building features, and probably the best advice we have at the moment is to spray those surfaces directly to wet them rather than spraying water up in the air. So this is to minimise the effects of wind. So for example, if you're protecting walls or windows, spraying directly at the top of the surface and letting the water run down the surface is probably the best advice that can be given at the moment. The standard 5414 does give water application rates, which are required for BAL 19. That's the level of hazard that you'd be facing. But there's not much quantified guidance on how to adapt that to other hazard levels, which we're hoping will be improved in the standard when it gets updated. Another important point is that if you are spraying windows, it's very important to wet the whole surface of the window so that you don't introduce thermal shocks which can break the glass if part of the window is cooled and the other parts aren't. So the next step is then to think about what types of sprinklers would you install and where would you put them to deliver that water requirement. And this is where considerations of wind drift, evaporation and splashing and runoff are really important. And it's important to consider that the conditions when you're testing the system are not going to match the conditions during a bushfire. So bushfires come with very hot, dry, strong winds. And we've got some modelling which shows just how large of an effect that can have. And then the aspect of the design that we know the most about, or with the most certainty, is the design of the water supply systems. So we do know you need an independent water supply and a means to move that water without relying on the mains electricity. We know that tanks need to be metal or concrete. Plastic tanks will melt in the bushfire. Pipes need to be metal or buried more than 200 millimetres under the ground. All fittings and pipes need to be of that construction. Even if you have one plastic fitting in the system, that could be the weak link that makes it fail. There are some signage requirements in AS 5414 which are probably advisable because it helps, for example, fireys when they come to your property understand the system and how to use it. And considerations of how the system's going to be operated. So it's important to integrate one of these systems, if you're designing one, into your bushfire survival plan. It's definitely good advice to have a written bushfire survival plan for your house and to think through the steps of when you would activate the system, if you plan to leave, when you would leave, and making sure that's early enough, because leaving late is one of the worst things you can do. And some avenues of ember ingress, like for example, if you've got a vent which isn't screened, it's doubtful that the sprinkler spray will protect you from embers entering the building and lighting it from the inside. which is one of the main avenues of ignition of buildings during bushfires. So it's not a silver bullet, and definitely needs to be sort of part of a protection strategy where you've got passive measures as well as potentially a sprinkler system. So the next few slides show some images from the research we've done. We've done some characterisation of different sprinkler sprays using a high-speed camera, measuring droplet sizes and velocities to understand sort of how the characteristics of the sprays, and then this allows us to simulate those sprays in computer simulations where we've got wind and heat and sprays around a building to see how they would perform. We've done some validation of that type of computer modelling. So we've run tests outdoors. This is a 2.4 metre cube, which we put out in a field on our campus. And during windy days, we were measuring the characteristics of the wind at different heights using this mast. And we'd have a spray mounted somewhere near the cube. And we were measuring the quantity of water hitting parts of the cube surface with these sort of spray collection devices. So that was just generating some simple data, which we could then compare to computer simulations to check that they are accurate. This is then comparing those experiments to the simulation. So we're looking at 4 different scenarios, which are shown in the photos and the simulations on the right as well. And we're comparing the results from the experiment on the horizontal axis with the result from the simulation in the vertical axis. And so this is the kind of research that was done decades ago for other types of sprinkler systems, and we're just starting to do it for bushfire sprinklers now. So overall, through this process, we developed a simulation method which we can trust. With some uncertainty. There's always some simplifications which go into these models. It's not just the upwind and fire-facing surfaces of the building that are at risk. There's also embers will circle around and settle on the leeward side as well. More recently, we've also been running tests. So the Australian standard AS 5414 has a effective wind on spray pattern test, which it specifies. And so technically, for a system to comply with the standard, that particular sprinkler type and spacing and mounting location needs to have been tested to this test. But the standard was put out in 2012, and we're pretty sure that last year when we started running these tests, we were the first people to have run them. So as far as we know, no other sprinklers have been tested to the standard. Here we're showing the effects of that crosswind. So the black markers are across the width of the wall, how much water was collected with different sprinklers. And then the red marks are showing the same test but with the wind flowing from right to left. So I guess the main thing we're showing here is that for some systems you get a similar kind of spray pattern between black and red, but for other types of systems, and especially these 2 systems are where you've got nozzles mounted sort of 2 or 3 metres away from the wall spraying up towards the wall through the wind, you get really big effects from the wind. So it's showing that, as we suspected, and as simulations have been showing, if you put the sprinklers sort of close to the target surface, spraying over a short range, that's probably the most effective approach. This is showing the same kind of comparison, but looking at water deposition on the wall, on the ground in front of the wall, with no wind and then with wind. So again, you can see a pretty big change from really even coverage to very skewed and displaced coverage. We're also looking with that test rig at the effects of water shedding features on the building envelope itself. So a lot of the building envelope is designed to shed water away, like windowsills, weatherboards. So we're looking at, as compared to a flat surface, whether these surfaces need to have sprays applied in a different way. And there's no conclusive result from that yet. We've looked at 3 different sprinklers. 2 of them did shed quite a lot of water away, so you would need to spray more water at the wall to protect it. But the other one, actually, the spray adhered better to the wall with the weatherboards. And we think it's because it was an impact sprinkler spraying at the wall. Normally it splashes a lot where the jet of water hits the wall. But when the weatherboards are there, they sort of restrict that splashing. So some of the key results from those tests that we've run, water delivery efficiency for these types of systems is typically in the range of 9 to 46%. of the systems we've tested anyway. So it's less than half the water you're spraying is actually getting to the target surface. Again, spraying water over a short range onto the target surface seems to be a good approach. Different sprinkler types can have different applications. So depending on what features on the building you're looking to protect, you could look at different types of sprays. It's not a one-size-fits-all. Wind effects can be really significant, and I've got some more results to show that in the next few slides. The application rates in the standard currently seem to be quite conservative, so we've compared them to application rates required for drencher systems for structural fire and to a similar standard over in the US, which is put out by an insurer, and they're sort of 2 to 5 times higher in our standard than they are in the other standards. The Australian standard specifies the amount of water that actually has to be on the surface, whereas the other standards specify the quantity of water that needs to be sprayed from the nozzle. So to compare them, you need to include that. So if you achieved better efficiency, like 80%, for example, then our standard would be even more conservative. But the best advice is still to follow our standard, I think, until they've been reviewed properly, which is hopefully going to happen in the current review. This is another small study we did. We developed a mathematical model just to look at the feasibility of whether when you have a cloud of airborne droplets around the building during the bushfire and you have flying embers coming in as well, what's the probability that a significant number of those embers could be intercepted in midair? And it looks like it's probably a very low probability because there were a lot of different claims about how these systems worked and not much evidence to back it up. So people were claiming this is how they work. But it looks like that's not going to be an effective approach. So it's better to wet the surfaces where the embers may land, and then they'll be extinguished there. We're still unsure about the best way to protect a building with water. So the best advice is to wet the building surfaces still, but there's all these other ways that it could be effective. So wetting the vegetation around the building. Airborne droplets can attenuate radiant heat, but through refraction. And that probably is part of how these systems work, but it hasn't been really properly analysed yet. We don't know how effective these sprays are at extinguishing piles of accumulated embers under bushfire conditions. So this is all still an area of active research. The last few slides I have are from the modelling we did for the Planetary Health Centre. We've put together some of these images which sort of illustrate how much wind affects sprays during bushfire. So we've simulated 6 different systems. This is one system. This system has 5 butterfly sprinklers mounted on the ridge of the roof. And the left-hand images are from a simulation under typical conditions, so that might be what it looks like when you're testing the system. The droplets are shown here in the top image, and you can see 94% of the water is landing on the roof when you test it. But then during a bushfire, under, I think it was a 54 kilometre per hour wind, 40 degrees, you can see how much those droplet trajectories are deflected. So there's a big portion of the roof that's no longer being sprayed. And then on the lower image, you're sort of seeing where the roof would be wetted when you're testing it in normal conditions on the left. And on the right, this is showing how much of a 40 kilowatt per metre squared radiant heat flux would be cooled or mitigated by the water flow. So putting sprinklers on the roof this is showing that those types of sprinklers are just a lot of the spray is going to be blown downwind. So I'll run through the other types of sprinklers to show you which ones are less and more affected by the wind. These are the same 5 sprinklers, but now mounted on the windward gutter. So again, under normal conditions, you might see it wetting that part of the roof and the deck really effectively. But when the wind and the heat come during a bushfire, most of the spray is blown onto the building. The deck's basically unprotected, and the efficiency of the use of the water is down to about 23%. And then again, the same 5 sprinklers, but now mounted at the edge of the deck on 1 metre uprises. You see the deck looks like it should be fairly well protected when you test the system. It still is protected relatively well, but there are some hot spots, and the wall is definitely not being fully protected. So we're down to about an 18% efficiency of use on the deck. Impact sprinklers, so these are developed for irrigation and they're designed to be resistant to the effects of wind, so they shoot a really coherent jet of water. So we simulated those as well. This is 3 impact sprinklers on the deck. They were affected less, so you can see the spray patterns are affected much less in the situation with wind. The issue with these 3 particular sprinklers that we simulated was that they had fairly low flow rates. So where you can see the total flow rate of the 3 sprinklers here is about 50 litres per minute. The previous one was 170. So yeah, if you're putting these in, it's important to understand how much water you're putting out and how much water is getting to the surfaces. If it's blue, it means the radiant heat flux is totally mitigated, and so the temperature's not rising through time. If it's any other colour, it's rising, and so if the radiant heat flux was there long enough, it would ignite any combustible materials. So again, impact sprinklers mounted above the gutters, the same 3. So again, it's a very low flow rate in this simulation. And again, we see that they're not as badly affected as some of the other sprays, but now that they're on the roof, they're in higher wind speeds. You've got higher velocity flow around the top of the roof. And so that you are starting to see even impact sprinklers are being affected quite strongly. But still, because these sprinklers are fairly robust against the effects of wind, the efficiency of protection is up around 35%, which is higher than we were seeing for a lot of the other systems. The last 2 systems, one is just a typical pendant fire sprinkler, which you might see indoors in a commercial building. We simulated them under the eaves of the building, so they spray out a kind of bell-shaped 360-degree spray. They spray a lot of water, so this is 650 odd litres per minute for the 6 spray heads. And during testing, it looks like the deck and the walls are fairly well protected. And because you're putting the sprays close to the walls, even when it's hot and windy, you still get a lot of the water landing there. So they are effective, but because of the large flow rates through these sprinklers, the efficiency is down around 14% under those conditions. You've got 47% on the wall, 41% on the deck, and then 12% is evaporated or missing. So most of the water spraying down onto the deck and walls. And then the last system we simulated was using flat fan sprinklers. These are similar to what will be installed on the windows here on this building. So these are mounted under the eaves and pointing at the top of the wall. So that's trying to get that film of water flowing down the surface. And during normal conditions, it looks quite effective. And during a bushfire, it still is fairly effective with about 36% efficiency. It's illustrating that principle of trying to deliver the water to the surface and let it run down the surface to protect it, that seems to be the best approach. Sprinklers on the roof, expect them to be the wind to have a really strong effect on them. Different types of sprinklers, the impact sprinklers are relatively resilient to wind effects, but they will still be affected, whereas anything that produces a really fine spray or a mist is really going to be affected strongly. So this slide, I was just coming back to touch on, I guess the key points are in terms of how much water is needed and where to put it. We know some things with some certainty here, but it's still evolving, our understanding. So like I said earlier, we don't know yet whether it's worth spraying a lot of water in the bush or not. There doesn't seem to be good evidence supporting that or not. Design for wind and evaporation is very important, and the design of the water supply systems, we know a lot of that with quite a lot of certainty. So following those general principles is really important. And then moving forward, this research is still going on here and overseas. Those images on the slide are from a really large wind tunnel in the US where they can build a whole building inside a wind tunnel and launch embers at it. So we're hoping they'll have it sounds as though they'll be testing some sprinklers in that facility soon, and we'll have some full-scale tests run in Australia soon as well. So over the next 10 years, I would expect the science backing up this kind of systems to really be evolving a lot more. Thanks, that was all from me.